We're live. All right, January 19th. I had a thought. I got to talk about this one more time. Okay, with a very basic example. Okay, so for people watching on the video, you're going to have to follow me around here because the example is actually sitting here on the table, so I'm going to have to repoint. And you're just going to have to listen to my voice here. There we go. Okay. This is my example. A hammer and a nail. I'll just get this started there. Okay? How many have hammered a nail before? Okay. I'm not sure I can really drive this thing in one, so I might have to hit a couple of times. All right, so. Okay, didn't do the greatest job, bent it right at the end. But now I can go back to the board. So now I'm looking for input. What does this have to do with the whole process of what we just did there? Can somebody give me a connection? Okay, Levi?
They were short, had 4 strikes.
Okay, go again.
Hitting the hammer very hard but very quickly.
Okay. So, there is actually, I'm going to go into 2 different layers. Because most people would focus on the hammer hitting the nail. And when they look at that, they say, well, the hammer hitting the nail drives the nail into the wood. And that's not an incorrect connection. What does the hammer have here that, well, let's go with this. Which variable in here is the one that drives the nail into the wood? If I only let you choose one of these, which variable is most responsible for the nail being driven into the wood? Julian?
Maybe force.
I'd go with force. Okay? So, I want the nail to be driven into the wood. So which one do I want? Do I want it to be big or small? We want it to be big. Because if it's big, then there is more newtons of force that would drive the nail into the wood. Now, in order for us to end up with a big number over here, what does that mean about this over here as a number? Do we need it to be big or small? Ben?
It needs to be big.
It's going to be big as well. Now, what object is this referring to in our process? What has the mass and the velocity that leads to the force being applied to the nail?
The hammer.
The hammer. Now, where does the hammer get this momentum over here? This is where we're really going to get into multiple layers.
It gets momentum from you swinging it.
Correct. And, I'm going to see if you guys get this. And I'm going to change colors here. let's see, I'm gonna do this in a different color. That I actually apply an impulse on the hammer. Now, when we talk about this here, this is like the follow-through concept that we talked about earlier. I would, if I was a perfect hammerer, I would want to bring this through a long stroke because that would allow me to apply a lot of force for a lot of time, which would make my impulse on the hammer big. That impulse on the hammer becomes the momentum that the hammer has initially. Now at the end, after the hammer hits the nail, what is its velocity? Because usually it's
0.
It's 0. So all that change in momentum then becomes an impulse that the hammer now applies onto the nail to drive the nail into the wood. So we actually have all of the things that we kind of talked about the other day, but depending on what aspect you're focusing on, the hammer is the object that I act upon to give it momentum, but then it becomes the agent that acts on the nail in order to drive it into the wood. So this idea of impulse and a change in momentum, sometimes the same object, depending on where you are in the process, could be the object or it could be the agent. So the next time that you have to hammer something in, this is kind of an elaborate example. Most people would just focus on the hammer hitting the nail, but the idea is that that hammer, which undergoes a change in impulse or a change in momentum that becomes the impulse to act on the nail, that only gets that because the person first acted on it to begin with their muscles to give it an impulse to cause that change in momentum. So I thought I brought that one up simply because I consider it to be kind of an everyday example, because we are always going around pushing things or hitting things. Every time you're doing that, you have this kind of situation coming into play. And sometimes that same object, as I mentioned earlier, sometimes it can play a dual role depending on where you are focused in the whole process. Okay. I don't know. Anybody actually hammer a lot? Okay.
Ironically.
Where?
Just like if I need to hang something up in my room, I'll just
Okay.
stick a nail.
Now you're probably not like smacking it like this, right?
No.
More careful. Okay, now homework stuff. Pointing to these problems, these were your level 3 practice problems. So hopefully you've taken care of that. And on your conversion problem from Tuesday, I'm going to say I feel like I took it easy on you a little bit by starting you off with one of those 3 subunit structures, so that all you were really doing was 3 individual unit conversions within the overall problem. So just be prepared for those types of units that have something squared or cubed in them. So if you've practiced those and you've gotten them right, hopefully you're in good shape for the future level 3 conversions here. Now the other thing that I need to put up here, and I'm going to put this over here as 5th period physics. I have given you a momentum packet, and we have gone through 2 kind of subtopics of momentum. One was just the concept of momentum, which was related to P equals M times V. The second thing was we went through this impulse momentum concept. And that involved the equation that I just had up here. Now, I would like to do a homework turn-in from this front side. And remember that the idea of the homework problem turn-in is that I'm going to put up a selection of problems that you definitely should have done. And on the day of the homework problem turn-in, I'm going to give you a blank half sheet of paper. And we are going to choose, kind of randomly, one of the problems off of the list. And when we choose the problem, the idea is that you'll have like 5 minutes or so to find that problem in your notes, copy your work onto the half sheet of paper, and then hand that in to me. Because I don't want your whole notebook, and I don't want you to rip papers out of your notebook. But this will be proof that you did the problem, because then you can just copy it over onto the piece of paper. So this will be a good practice run for us, because I don't think any of these problems was really super elaborate. They were all pretty focused. So out of the problems for momentum, these are our problems that we will say are the possible ones that you might have to copy over, because we're only going to do one. Let's see. Okay, so there's a total of 7 of the problems that will be the possible turn-in problems. So if you have been on top of this and you say, I've already done all the ones that you told us to do, you're in good shape. If you have not done those problems, then you're going to need to be sure that you have these ready, and we will go ahead and say Friday. That's the 21st. Okay? So, all right, thank you.
That's one.
Tigran.
So
All right.
that's when the Turnitin would be.
You are turning in one of them.
Okay.
So you have to have them all done.
Okay.
Okay? Does anybody have any questions on that one? Okay. So this will be the first time we're doing the homework turn-in. But again, my goal is not to have you turn in this huge piece of paper and I have to sift through it to find some problem. I'm going to ask you to just turn in one of those. But the idea is that you already have it done in your notebook so that you can just hurry and copy it onto that half sheet of paper and turn it in. So there should be no need to, like, I need a calculator. You don't need to do anything. Put your name on it, find it in your notebook, and then start to transfer it over. Yes, Gage?
Are pictures fine? Like pictures
No.
of our...
You are going to write this out.
Okay.
Okay, that's why there's no, well, let me look at my picture on my phone to copy it. It's like, nope, that doesn't work. You are copying it from, I want a hard copy in your notebook done. And that's what you would copy from. Okay, so far so good? Yes, Nick.
Go to the bathroom.
Yes. Is somebody already out, or did somebody forget to turn that thing back? I think. All right. Just remember to flip it back when you get back in. Okay. So today we are going to start in on what I would call the second half of our unit on momentum, and this has to do with what is called the law of conservation of momentum. Let me sure we got plenty of time. Yeah, we're good. Now this is the first time we're running into one of these things that's referred to as a conservation law. There are a few of them in science. Does anybody remember one that they would have been, I think, exposed to in chemistry? Levi?
Conservation of matter.
Conservation of matter. Now, was this from chemistry?
I believe so.
Okay, and if I were to ask you, if someone said, oh, I know this conservation law, my follow-up would be, could you either give me an example or give me kind of a breakdown as to what's the idea behind that law of conservation that you mentioned? Could we go there?
The amount of matter stays the same regardless of its form.
Okay, so if you were doing a chemical reaction, and let's say, now I'm making this stuff up again. If you had 4 grams of one substance, and it was going to completely react with 5 grams of this other thing to make a final product, how much product are you going to have?
9 grams.
You're going to have 9 grams. Okay? Now, this idea behind a conservation law, I have my way of summarizing what it means. And it's kind of based off of this idea of there's a before, and then something happens, and then there's an after. And the idea of the conservation law is that however much stuff you're talking about that you had before, when everything's all done about whatever the hell's going to happen, you will have just as much stuff after. Now, does this product, in a way, is it going to look exactly like these two guys? Most likely not. Okay? But we'll have the same amount, at least in terms of mass, of that stuff. Okay? So that's one thing that you may remember, because they do teach you that in chemistry. If you have a certain amount of reactants, you're going to have the same amount overall after. Can somebody give me an example, not necessarily a scientific one, but some example that they think parallels this conservation idea? And it doesn't have to be a sciencey thing. Because we're going to focus on momentum, but I just want to get the idea here. No? Okay, let me give you a hint. Let me give you a hint of something that's more of an everyday thing. How about money? In what sense could you maybe make an example out of money and what you do with money to try and illustrate a conservation law? Okay, Ilya.
It's like inflation and deflation.
No,
Basically,
that's
like
not what I'm
something
thinking of.
increases.
I give you $20 and you go grocery shopping. And you come back and let's say you have $5 change. How has that money still been conserved? Because some people might say, oh, I only got $5 left. In what sense has that money still been conserved?
The money wasn't destroyed, it was just given to the cashier.
Right. And because it was given, it changed form into what?
Into the food that you got from
Into the food that you got. So when you think of the concept of shopping in general, that is a type of monetary conservation. Now you might say, oh my God, I went and spent $50 on a shirt. I got ripped off on that. That's beside the point. That was, you made a poor choice as to what to buy. But the idea that you said, I had $50 and you went in and you walked out with a shirt, technically from a monetary perspective, people would say, well, you're still balanced. You still have just as much monetary value, at least according to price, that you had going in. You just don't have the cash now. It has changed form, and now it has taken on the form of a shirt. So when we exchange money for things, that is a type of everyday conservation concept. That, because sometimes people say, oh man, you blew all your money. Well, the only way that you really lose money, literally, is if you lose it and it's like you dropped it somewhere. And even then, is it truly lost? Not really, because if somebody else finds it, they got your 20 bucks. And we could play a little game here where we could say, look, let's say if I each gave you $1. Well, how many would we have? We'd have about $28. If we then said, okay, go talk to people and see if you could like talk to somebody out of their dollar, you know, so, oh, I need to get food, I'm really hungry, and they're like, oh, okay, I'm taken care of, here's my dollar, you know. So one person ends up with $5. That means that other people don't have their dollar anymore because they were willing to give it to them. And overall, we still have the same amount of dollars, it's just been like redistributed amongst the people. That's the idea of the concept of a conservation law. This is going to sound super hokey. Amount of stuff in the beginning equals amount of stuff in the end. Okay? And one key word that we're going to employ here in this law is this idea of the beginning. This is our initial, and on the other end, this is going to be final. Now I have some other examples specifically for momentum that I'm going to bring up here in a minute. But this is the idea in general of a conservation law. Any questions so far? Everybody's got this like copied down now. And you can always go, you can always watch the video so I can know people like looked at it so I can see that it has views. Kind of depressing when I like check out my little channel and I got 0 views on my stuff. I'm like, oh man. I'm not jazzing it up though. Okay. I'm erasing.
No.
What?
Sorry.
Okay. I almost want to say, go ahead and take a picture. But keep writing. We're good? All right. I always know when I do it, I'm like, okay. That was the unscientific approach to the law of conservation of momentum. So now we're going to take the scientific approach. How many people know what that symbol means? Okay, what is it, Gage?
Sigma?
Sigma, and what does it mean you're going to be doing?
Destroying the betas.
No. Julian?
Doesn't mean adding to
It means you're going to be adding a bunch of stuff together. Sometimes the sigma, they refer to it as the summation symbol. Okay? So I'm going to write a mathematical example here, and then we're going to kind of break it down, and then we're going to talk about an example, and hopefully you go, oh, I get the idea. And that's a lowercase p. We got that. So if I stopped right here, could somebody tell me what this says? Okay, Levi?
sigma initial momentum.
Okay, and the sigma means like adding everything together. Sometimes they'll just say sum of. Okay? So when you see this, you can think the sum of, which means you're just going to add a whole bunch of things together. So this literally means the sum of the initial momentum. On this side, we have that. What does this side mean?
The sum of final momentum.
The sum of the final momentum. Now there's one thing we really haven't delineated in here, and that is the idea of a system. And this I'm not going to leave up for long. This is pretty, and this concept is pretty basic. A system is a collection of objects or materials. Okay? So the idea behind this expression here is that this literally says the sum of the initial momentum of a system has to equal the sum of the momentum, the final momentum of that system. Now, there are a variety of things that could be in that system, but usually what we focus on are objects that are in the system. So I'm going to erase this now. And we're going to expand this a little bit. Now this is where this may or may not make sense depending on if you've played around with this before in math. This summation symbol means you add a bunch of things together. So I'm gonna write something out here and then we'll explain what this means. And I think we'll go to 4. And then do our dot. Now, trivia question. Anybody know what the 3 dots are called?
An ellipse.
All right, ellipses. Okay. Why do you know that?
I actually don't know. I can't really remember.
Okay. Sometimes I have some students who go, this teacher made me learn. So I was like, okay, credit that teacher. Okay, and hopefully we all understand this means this could go on and on and on. So, let's see if you can make sense of what this means. What would P1I represent? Anybody want to take a gander at that one? What does the P stand for? Come on. What does lowercase p stand for? Momentum. Okay.
I was gonna say like the initial momentum of like object number 1.
Perfect. What's P2I then? Keep going.
The initial momentum of object number 2.
P3I?
Initial momentum of object number 3. Initial momentum of object number 4.
Okay. It's our system. Okay? And this simply represents all of the momentum we have collectively. Now, right now, if you're going, well, does object 3 have momentum or not? We don't know yet, because we're just talking about this very conceptually. On this side of the equation, this is what it would look like. Okay? Now, somebody other than Michael, can you tell me what this term means? Somebody. Okay, Alexis. Perfect. And this one? All right. Right. Okay. Now, when we go, what happened at this equal sign? something happened. And that caused this system and these objects to interact with each other. So on the left, this is like the initial state of the system, and on the right, this is the final state. But the idea behind the law of conservation of momentum means that however much momentum we have over here to start with, we're going to have the same amount when we're done. But the objects can interact with each other. So I'm going to give you an example of this, and hopefully you'll go, oh, I get this idea. Okay. Anybody have an idea what we're talking about? Gage?
Is it pool?
Correct. What do you think the most common wrong answer is?
Bowling.
Bowling. Okay. What distinguishes this from bowling? Let's see. Okay.
The setup.
Not really.
Number of objects.
The number of objects here. How many do we have?
15.
15. If this was bowling, how many would we have?
10.
We'd have 10. Okay? Now, this whole thing is our system. How many people have played pool before? Okay. How many people have been responsible for the break? How many people have ever been nervous about doing the break? Because if you screw it up, you look really bad. Okay. Now I'm not going to say that I'm great at a break, but I will tell you, way back when I was younger, I absolutely sucked. And it wasn't until I went to junior college and I rented a house with some friends that happened to have a pool table in it. So we would regularly play pool. And so I was able to watch different techniques. And little by little, I was able to get better at this. But I can tell you, I was petrified when someone said, okay, it's your turn to break. Because what does a good break look like? What does it do?
It separates them all.
It separates the balls all over the place. And in the end, what's your hope?
One gets in the goal.
That one would fall into a pocket so you can retain control of the board. Now, if this is our system, and think of this concept right here, how many individual P's would we need to have on the left side here? Matthew? Close. Why 16? Because of the cue ball. And what is the nice thing about the value of 15 of the object's momentum? Because this is before the break.
They're still.
They're stationary, so how much momentum do they have? 0. So technically, we would have 16 terms over here. But how many of them would actually have momentum? 1, and that would be the cue ball. Now, when the cue ball comes down here, and I'm going to do this in a different color. The cue ball gets here. Let's keep it simple. Let's pretend that the cue ball comes to rest because it hits the racked balls. How much momentum will the cue ball have then after the collision? If it comes to rest? 0. So if people only focus on the cue ball, they would say, oh, the cue ball lost all its momentum. Why has it not lost all its momentum? What happened to it?
momentum transfer to the other pool balls.
Right. And what happened with these pool balls, which I cannot really properly illustrate in this picture because it'd be too complicated. What do?
They scatter across the board.
They scatter all over the place. Okay, so I could draw a bunch of arrows that point like all different directions because that's what you hope to have happen. So the momentum of the cue ball or the system is maintained, but the momentum is transferred to the other objects in the system. And this is the idea, or this is an example of this idea of law of conservation of momentum. That you start with a certain amount of momentum, and then something happens. And in our case, the something happens is usually a collision of some type. And after the collision, things look different because now these 15 balls look like they're going all over the place. But if we could meticulously keep track of their individual momentum, all 15 of the ball's momentum would add back into the single amount of momentum that the cue ball had after the player hit the ball. So if you were to ask most people, how do you perform a good break in pool? What would be the main common thing that they would tell people they needed to do? Nothing? No? Do you think they'd say, hit this ball hard? If you don't hit this ball very hard, are these balls going to scatter very much? No. So most people would say, hit it hard, man. Now that's what makes it a little challenging, because if you're not very coordinated and you don't hit it dead center, the ball goes God knows nowhere. It might not even hit the damn racked balls. But the harder you hit this, what do you give it more of? What?
Momentum.
Momentum. And the more momentum this ball has when it gets to right here, that means it has more momentum to transmit onto these 15 racked balls. And that means there is more momentum to be spread and disperse the balls, which means they'll spread out in a wider pattern. And again, your ultimate goal is to maybe have one of them fall into a pocket so that you can maintain control of the table. Now, we can even go back to my love of impulse and momentum, because when you talk about impulse momentum here, the harder you hit the ball and the more you follow through with the cue stick, the more impulse you give the cue ball, which gives it more momentum down the table to then crash into these balls and spread all over the place. Okay? Now, could you also apply this to bowling? Sure. What takes the place of the cue ball?
The pins. The bowling ball.
The bowling ball. And what takes the place of the racked balls?
The pins.
The pins. And the harder you throw the ball down the lane, it gives it more momentum. It scatters the pins all the more aggressively with the hope that they all fall down. Okay? So, this is your introduction. We are going to have to build off of this. Okay? Because we don't have a way of measuring momentum directly. So we're going to continue with this tomorrow because we need to break this down a little bit further before we can actually do some problems with it. Okay? So, that's your introduction to the law of conservation of momentum.